What are the magnetic field strengths and directions at points 1 through 3 in figures 24.5? So this one. So the idea here is we have a couple of wires with a current flowing through them. And since we have a moving charge, that is going to create a magnetic field. And so we have this current flowing through this wire, and it's going to create a magnetic field around the wire. And the way we know the direction of it is we're going to use the right-hand rule. So you take your finger, your hand, and you wrap it around the direction of the wire, and that is going to give you the direction of the magnetic field. I know it probably looks backwards because of the webcam. Thumb, direction of the current, wrap your fingers, and that will give you the direction of magnetic field. So thumb this way, wrap your fingers will wrap this direction. So for the top wire, we're going to have a magnetic field into the board here, into the board here, out of the board there. And the reason I drew basically two into the board directions here is because that way it's easier to analyze region 1, 2, and 3. You'll see later. So I'll say current going this way. All right. So now we do the same thing with the second wire. So thumb along direction of current, wrap your fingers. So thumb this direction, wrap your fingers. It's going to be into the board, out of the board. All right. So now we can figure this out. I'm going to assume that point 2 is halfway between the two wires. So magnetic field at 1, I'm going to call this wire A, this wire B. It's going to be magnetic field due to A plus magnetic field due to B. Now what I'm going to do is I'm going to say into the board is positive. And so, actually, no, I'm going to say out of board positive. So basically, that one is positive. The influence from A on the first one is positive. It doesn't really matter as long as I keep everything straight. So positive. So we're going to do magnetic field due to A, which is the top wire, minus magnetic field due to B, which is the bottom wire. Because they're in opposite directions, it's going to be equal to magnetic field due to 1. So, yes, and that's the general idea we're going to have for this. And so the magnetic field due to a current carrying line is going to be mu naught I over 2 pi r. And this comes from Ampere's law, I think. It's just it's worth memorizing. And so when we take this concept and we apply it to this whole system here, magnetic field due to A can be out of the board. It's going to be mu naught I, I'll do IA, so we know it's current through A, all over 2 pi, and I'm just going to write RA, because it's it's the radius from wire A to point 1. And we're going to subtract from that mu naught IB, all over 2 pi RB. There we go. We're going to do some simplifying, and we're going to get mu naught I. Do they have the same current? They do have the same current. Excellent. Just opposite directions. Over 2 pi. And then the first one is going to be 1 over, I'm going to write this as 0.02 because it's 2 centimeters, and it's going to convert it over to meters, minus 1 over 0.06. And 0.06 is 4 centimeters plus 2 centimeters is 6 centimeters. simplify this a little bit. 4 pi times 10 to the negative 7 over 2 pi. 1 over 0.02 minus 1 over 0.06. 2 pi and the 4 pi cancel a little bit, giving us just 2 up top. And we have 2 times 10 to the negative 7th times 1 over 0.02 minus 1 over 0.06. And for this, I'm going to use Wolfram, just because it's easier to use Wolfram to do subtracting fractions than it is to use like a calculator like a TI-83. And if I was a better person, I could do it in my head. I am not. 0.02 minus 1 over 0.06. And this gives us 6.7 times 10 to the negative 6. And that's going to be measured in Teslas. All right, so now we're going to do the same thing for B2. B2, we're going to do all the same simplifications. So we're going to end up with 2 times 10 to the negative 7th, right down here, times 1 over 0.02, because this is going to be out of page. Because out of page, that gives us their direction. And this time we're going to do for wire number, or point number 2, we're going to do 0.02 or 2 centimeters as the radius, the distance for both of them, because both wires are 2 centimeters away. Also, both wires are in the same direction. I think I said into the board is going to be negative, but I'm not going to worry about that for now. The idea here is that they're both in the same direction, so they're going to add to each other. So I'm just going to go back to the same equation. I'm going to do, this time, I'm going to instead do, make big, 1 over 0.02 divided by 1.02, and we get 2 times 10 to the negative 1, 2, 3, 4, 5. I think 5. We'll check. So it's going to be equal to 1, 2, 3, 4. Yep, 2 times 10 to the negative 5th. 2 times 10 to the negative 5th. And again, Teslas, this is going to be into the board. So the direction here is going to be into the board. And now we're going to have same thing on B3. Same concept. So I'm going to come right down here. B3, we do the same thing. Mu naught I over 2 pi r, which is the magnetic field produced by a current carrying wire derived from Ampere's law. When we simplify things, we're going to get 2 over 10 to the negative 7th, 1 over radius 1, which in this case I'm going to say is, I'm going to do this in terms of the bottom wire. So it's going to be 0.02 minus, and the distance for the top wire to 0.3 is going to be 4 centimeters plus 2 centimeters, which is 6 centimeters, 1 over 0.06. And they're going to be in opposite directions, so there's a minus sign between them. And so we are going to get the exact same answer we got for the first one, which is 6.7 times 10 to the negative 6. 6.7 times 10 to the negative 6 Teslas. And this time, though, it's going to be into the page because the bottom wire is going to be stronger than the top wire. And the reason why the bottom wire is stronger than the top wire is because they both have the same current going through them, so that's not going to be the determining factor. But the bottom wire is closer, so it's going to have a smaller radius. And since you're dividing by a smaller r here, dividing by a smaller number gives you an overall bigger number. And that's why the bottom wire is going to dominate. And since they're opposing each other, the bottom one is going to dominate the reaction, the relationship. And so it's going to be into the board, where it's into the board due to the bottom wire, because the bottom wire creates a magnetic field into the board. So a little bit crazy. The way I usually approach these kind of problems is you first are told that you have a current carrying wire, and you talk about magnetic field. So as soon as you think of that, as soon as you see that, think of mu naught I over 2 pi r. The other similar equation you're going to have is current in a loop. Current carrying wire in a loop. That's going to give you I'll do a little O here for circle. That's going to be mu naught I over 2r, basically without the pi. The other equation you have is for a line, which is 2 mu naught I over 2 pi r. So it's just two common scenarios you see, worth memorizing if you're going to take the test. We then drew the magnetic fields due to each wire. So this is to the wire on top. These are the directions of the magnetic field, with into the board being the X, out of the board being the circle with the dot. And then in the middle, we see that they reinforce each other, and then the top and bottom, they oppose each other. So when they oppose, they have negative signs. When they reinforce each other, we just add them, and then we determine the direction of the final value based on which one is going to be stronger. We can go through it more rigorously, but I think that trying to have a conceptual idea and making the numbers work usually gets the right answer for me more often than if I just do it from a sterile, mathematic, clinical type approach. So that's how I did this one. I went through it kind of fast. Hope that helped. See you next time.